Everybody, it gives me a great pleasure, an absolute delight to host Dr. Vijay Chandru. I met Vijay very recently at the Indian Institute of Science and Art Park in particular, actually. But I understand that's his second stint, or maybe one of his numerous stints at the Indian Institute of Science, Vijay.
That's right.
Yeah, and his resume is outstanding. He's been one of these stalwarts in the area of biotech, life sciences, and healthcare now. His LinkedIn profile says he's a pioneer in the World Economic Forum as well, where he serves on the World Economic Forum's Global Agenda Council for the future of the health sector. But we all know Vijay for his association on Strand Life Sciences, where he was the chairman, and in that sense, bringing us into the whole life sciences genomic space, and I hope Vijay will talk about that today. In some sense, I share something common with him. I mean, I didn't have a biotech background before got into biotech. Vijay is also an electrical engineer turned computer science pioneer, and then moved out to life sciences and now healthcare. So yes, without much further ado, I give you Dr. Vijay Chandru. Vijay, please.
Thank you so much, Vipin, and Ravi and others for pulling me into this. I very happy to do this. Actually, just earlier this evening, we ran a panel for the Lancet Citizens Commission on reimagining India's health system, and basically we were talking about the Ayushman Bharat digital mission and the India health stack, and so it was. So this is slightly different. I'll kind of.
Josh Butler has been missing in action for a month, and now in the big match he's starting to stand up, boom down the ground.
Oh, someone's into cricket, I think. Okay, so. Is that good? Should I continue? Can you all hear me?
It's changed.
Tell me what you want.
Hello.
Should
I keep going? Yeah.
Please go ahead.
Okay, right. Yeah. So I was going to actually just take you through, sort of the technological building blocks that are getting us to where it's become, exciting to think about, what can happen with healthcare, and I think, I'll take you through a little bit of a historical sort of journey here, and then we'll also see some of the really emerging areas for entrepreneurial, opportunities and challenges. So, as was mentioned, I think, I've been at the Indian Institute of Science since 1992 or so in computer science, and then went off on an entrepreneurial journey, and then have come back to the institute. I'm an old timer. I actually was inducted into computational thinking, cybernetics by Stafford Beer, who was visiting BITS Pilani when I was an undergraduate, and he was one of the founders of cybernetics. And so I think I jumped into what is now called intelligent systems or AI very early on, probably in the mid 70s, and when it was still sort of in formation. And it's been an exciting sort of journey, and I guess for most of us, involved in TiE, and this is this is the journey that's been exciting, and we are now at this point where this explosion with AI and cyber physical systems has really sort of brought us to a really accelerated situation with technologies and enterprise. And what I wanted to just alert people who have not thought about this, that there have actually been two exponential laws that have been driving this explosion, and they've been not quite side by side, but pretty close to being concurrent. And one is, of course, what we all know and love and live by, which is Moore's law, which has been giving us all this power to do everything from just straight computation to GPUs and deep learning and etc. And then we have Flatley's law, which is like Moore's law is named after the chairman of Intel. Flatley's law is named after now the chairman of Illumina, Jay Flatley, and it's really this exponential drop in the cost of genome sequencing. And as you can see, it's actually moved faster than Moore's law. After an inflection point around 2007, when Illumina acquired next-gen sequencing developed by Solexa at the University of Cambridge. So this has been a very, very exciting, exponential law that has been driving new ways of thinking about living systems, right? And I kind of merged the two timelines in some sense, so we'd actually see this side by side. You basically have, just around the time that universal computing machines and the mathematical theory of communication is being laid out, people discovering the structure of DNA and then figuring out how to sequence. And so you have Watson Crick, Fred Sanger, and then the Human Genome Project, which is a little bit like the internet, right? The internet was a huge public good that was created by massive investments, which I guess the wealthy nations were able to foot the bill. And similarly with genomics, the Human Genome Project was done primarily in USA and UK, and essentially we have arrived now at a point where we're both thinking about precision, digital health, and of course extraordinary advances in AI and data science, right? So I think that it's a really interesting sort of correlated timeline in the history of science, as I mentioned here. And it's been somewhat, I feel extremely fortunate to, in some sense, have been able to work with both the revolutions, right? And of course, I'm not going to try to give you a biology lesson, but you all know that there is this thing called DNA, which is essentially the code and that's what the Human Genome Project was about, was could we actually get out the raw data, the raw sequence, and of the entire genome. Now that's about, it's 3 billion letters from end to end, and it's sort of in a double helix formation where the two strands of the helix are related. So information-wise, it's about 3 billion bits of information, and this information supposedly tells us how proteins are expressed. And since proteins are the workhorses of living systems, it's kind of holds the mystery of life, right? And so we are lucky that we actually have a map now to search these organisms. The DNA itself is organized into chromosomes, and as many of you have heard, there's a famous company called 23andMe, right? So 23 is the number of chromosomes, and that's where they picked up the name from. And actually, although this genome is a very big and very long sequence, we've really been working only with about 2% of the code, because that's really what we know how to, it's partly that we know how to interpret, and it's also the part that seems to be involved in the expression of proteins. Now, the remaining 98% of the code is not, I mean, people call it junk, but it's really we don't know how to interpret it. And I think more and more so we're starting to see that by getting whole genome sequences, if there is it opens up all kinds of new ways of thinking about discovery, particularly drug discovery. And so pharma companies are, for example, driving a lot of the development in genomics, and pushing for more and more whole genome sequencing. And so we roughly have about 2 million human beings being sequenced as we speak, and across the world. Of course, in India, the number is very small still. So there's great opportunity. Cost is still a bit of a challenge, but I think with exponential laws like Flatley's law working, it's only a matter of time before these things become very feasible to do, even here in India. And so the way current sort of sequencing technology works is that it you cut the genome into small pieces and sequence small pieces at a time. So this is called short reads, and then you have to reassemble that. And because you have the human reference genome, which was the big project done as a public good, you can align against that reference genome, and it used to be a tough computational problem. Today, we are able to do it in multi-threaded architectures with a lot of parallelism into the algorithms, and we can solve this in less than we can take it down to minutes on really powerful platforms, but even on good workstations, you can do it in less than an hour, right? And so you can align these sequences and then read the book, right, so to speak. Now, that's as far as reading the genome is concerned. Technologically, there's also been a challenge out for some time now on whether we can write genomes, right? And to begin with, I think the breakthrough has been that we can actually edit genomes. So we can go into the genome and do a cut and paste operation. So you can cut something out and paste something in. And of course, this technology is called CRISPR-Cas9 and CRISPR, really. And because there are multiple Cases that would be used, or different enzymes. Jennifer Doudna and Emmanuel Charpentier, who sort of developed this, originally have, of course, received the Nobel Prize. Now, this is starting to be used to actually, deliver treatments for genetic disorders, including leukemias and also birth defects, sickle cell, and so on, and thalassemia, beta thalassemia. The price point for being able to deliver these types of treatments runs into, over $1 million per patient, right? So it's still very, very expensive, but the technology is showing that these things are possible. This technology not only helps with human health, but can also be applied to, plants, animals, microbes, and you can have designed microbes for cleaning up the environment, for energy generation, and all kinds of, very neat applications. And so this is starting to be seen as a very big breakthrough. And later we'll talk about the actual economic opportunity. It's felt that this genomic revolution with these applications in therapeutics and industrial biotechnology will go into trillions of dollars. I mean, it's Goldman Sachs estimates about 4.8 to 5 trillion as the market for the products coming out of this. So there are other very interesting interplays between biology and computation, and I think computational systems biology is another very, very exciting area. So at Strand, we actually built a model which is a dynamical systems model, about 200 differential equations to model the dynamics of the fluxes in the liver, and so by using this model, we are able to predict hepatotoxicities. So livers get affected by chemicals that you ingest, and drugs are, many of the drugs that you take, even for health reasons, could really damage the liver, and many drug candidates fail because of toxicity in the liver. So being able to do this with information technology tools actually can really accelerate drug discovery. And this particular platform that we built sits today in Syngene in the Biocon group and is used for profiling of hepatotoxicities of chemicals. Genomics itself has come into the mainstream of precision health. I think what you might call clinical genomics. There have been many cases now, and that have been documented well, of how by analyzing the genome you can essentially change the course of treatment, be able to use a quantified self approach to kind of anticipate and predict your own illness, like Larry Smarr sort of predicted Crohn's disease about 2 years before it manifested in himself. Professor Smarr is an astrophysicist by training, who's sort of been one of the leading lights in this whole quantified self movement. It's of course now almost a retail thing, right? Everybody talks about quantified self as something that you put on wearables and measure, and but it was a big deal when it was started. And as I mentioned, I think the overall impact of genomics economically and from an entrepreneurial perspective can be really massive. I think the challenge is that, in many of these cases, you're sort of opening up new markets and, and it requires a certain staying power or, or the ability to create opportunities and take this forward. But it's really an immense opportunity. And the interface between digital and biology coming into play into healthcare is what is exciting about this. So we also saw an extraordinary interplay between some genomics, but mostly AI and molecular technologies coming together for rapid sort of vaccine development during this pandemic. And and I think in history, this pandemic will be remembered for the fact that it was probably one of the first times that we were able to go from understanding what was the pathogen to actual vaccines that could be delivered within 11 months, right? And if you look at typhoid or meningitis or mumps or hepatitis B or whatever, the time that it took from recognizing what the disease was caused by to coming up with a vaccine was far longer. And I think, of course, the emergency because of the pandemic situation. Well, but pandemics were kind of was the fear even with many of the other pathogens here. But we just didn't know how to do this rapidly, and I think these exponential technologies have helped with that. If you look at the World Economic Forum's list of sort of 10 emerging technologies, this is a couple of years old now, but you could see that there's healthcare and digital health is kind of right up there, and including whole genome synthesis, which was, of course, it comes from that ability to do genome writing as well as beyond genome reading, of course. I'm just going to try to wind up here with I think this was actually a slide that I had made some time ago when I was talking to a group of students in the MBA class at Columbia University in New York, and in a strategy class, and they asked me to make some predictions about 2050 and what we might see as being sort of technologies that could make a difference. And of course, the idea that biology and engineering can come together was actually the most exciting thing when you start thinking about the next 30 years, right? Because I think the last 20 years have been exciting because of biology and information technology coming together. But now think about nano, new materials, and all kinds of new technologies and engineering techniques that can also be brought to play. And the predictions are laid out there. They're obviously a little bit of crystal ball gazing, but I do believe that we have an opportunity to actually save the world, right? I think, and I think technology has to play a role here. I think the planet is actually in a crisis, and I think it's so we have to all think of ourselves not just as entrepreneurs trying to build successful companies and become so-called unicorns and so on, but also in having impact to actually make the world a better place. So I think really hope that I've been able to convey the message that this is a very exciting time for all of us, because we're I guess in a position now to leverage these extraordinary exponential technologies that have been developed for us, and that we can now think really out of the box and really think about how to build sort of recombinant innovation where we put things together to create solutions for various challenges. Just by way of readings, if you really want to get to know more about genomics and particularly clinical applications of genomics, my co-founder, who's now the CEO of Strand, Ramesh Hariharan, has written a brilliant book called Genomic Quirks. It's available on Amazon. It's published by the IISc Press. So it reads like a Sherlock Holmes novel, right? I mean, it's written like detective stories, and so you can really read one chapter a night, and you'll also learn a lot about genomics. The Creative Destruction of Medicine, Eric Topol's book, this was really his first book on this theme. He's gone on to write several others. The Patient Will See You Now, and Deep Medicine, and so forth. But this was really sort of a groundbreaking book. And in fact, he helped us and reviewed Strand back in 2012 when we were just beginning to get into precision medicine. He was one of the reviewers. And this is a new book, Jamie Metzel's Hacking Darwin. And I think if you really want to understand what CRISPR means and where it can go, I think it's a wonderful read. So I really recommend that. The Age of Living Machines is my last slide on what the future can hold. And this is written by the former president of MIT, Susan Hockfield, and again, fascinating book, and it's received many awards and so on. So these would be my recommendations. And let me just end as an entrepreneur with a note of appreciation. The four of us who founded Strand, we're all data scientists by training, but jumped in and created a life sciences company. We were all professors of computer science at the Indian Institute of Science. We also happened to be the first professors in India to start a company. So this was celebrated a few days back at the Indian Institute of Science. Strand is now part of the Reliance Group. Reliance acquired a majority position in Strand about 6 months back, and so now we're embedded in the Reliance Group, and we're looking forward to an exciting ride with the large industrial partner that Reliance represents. And with best wishes to all you young entrepreneurs who are jumping into healthcare, and particularly at this interface of IT and health, I think this is really a great opportunity, and wish you all the best. I'll end there, and let me stop sharing. So yeah, if there are any comments, I'd be happy to respond. So.
Thank you, Vijay. That was a phenomenal presentation.
Sure.
We've covered a lot, and I hope I'll leave it out to the audience to ask questions. Anybody? I think it is because of the time and
sure. Yeah.
something happened with the system. It locked a lot of the participants out.
Oh, okay. Yeah.
That I noticed, and I had to unlock thanks to somebody writing to me saying that that it's locked. But in the end, I think it was a fabulous session. So, anybody got questions? Maybe I'll ask one, Ravi.
Sure. Go ahead.
We are at a similar stage. What made, and one of the things that I left out also, I realized, was your association with the computer.
Right. Yeah. Same group of faculty.
The gang of four?
Yeah, the same gang of four. Yeah.
How come? How did you folks decide to get out of ISC as professors and start something? What was the vision that you had at that time? Do you envision that you would create such an impact here in India with Strand?
Yeah, actually, so around the mid-90s, I think we came together and we started running a lab together. It was called the Perceptual Computing Lab. It was a bit like the Media Lab at MIT. I think we were we built a lot of solutions together. We did a lot of consulting, with companies both in India and in the US, and we were having fun doing all that. And then we sort of dreamt up of the computer and was starting to build that when Ratan Tata came to IISc as the president of the court. And usually somebody from the Tatas is the president of the court, and this was his first address to the campus in 1999, I think. And he said, I travel around the world and I visit many top universities, and IISc has always struck me as good, if not better than many. But I don't see startups, around the campus the way one sees at MIT or Stanford or wherever. And so we, that night, my colleague Swami Manohar wrote to the director of IISc and said, Perceptual Computing Lab is ready to start companies. What is the process? And so the director was quite, disarmingly honest. He said, we don't have one, but I'll appoint a committee. And and then we went into a whole process. It took about a year, but we actually started two companies. The computer was almost ready, so we launched a company called Picopeta Computers and Strand. Strand was a little ahead, about 6 months ahead. Ramesh and I sort of focused on Strand, and Vinay and Manohar focused on the computer company. So that's how we got started. But we actually expected to have many more coming out of the lab, but I think these two sort of took enough energy that we didn't actually venture to commercialize other technologies that had been developed. So that's the story in short. But yeah.
Oh, that's pretty cool.
Right. So
I don't know if you have any more time. I'll let the organizers, Shreya and the others who are on call, to let us know if there's time for any other question. I noticed among the members there are some of them from my team, or a lot of them from my team. There are a bunch of data scientists as well. I don't know if they'd like to ask any question with regard to that. Anybody? I think we'll.
I think it's late at night, so right.
Let's call it a night and a whole day.
Yeah. Okay. Great. Thank you for joining. Those who did. But yeah.
Pleasure having you.